So then your equation is A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught is equal to 0. And x naught, y naught, z naught, you can choose to be any of the 3 points. It doesn't matter which one.
That means so.
Okay.
I'm really low.
I should hope so. Okay. Alright. So then this you can then write as z being a function of x and y. So that gives you a function that defines the top of the tetrahedron. So that's where your limits in z come from, and then here you use these edges and the extent of this base of a tetrahedron right here to figure out the limits in x and y. So for instance, you could choose constant limits in x, and then your limits in y will be functions of x. Or you can go the other way around. The degree of difficulty is exactly the same either way. Questions? Okay. All right. Number 7, mostly verbal. So sphere with a hole drilled through it, using cylindrical coordinates. So what I'm going to do is at least provide some visualization like the other ones. Looking at the sphere from the side. So, when you're cutting out a portion, as a cylinder from a sphere, you have to be careful. It's not this rectangle here. That's not what you're cutting out. Really, it's this part. So you have to take into account the curved tops of the sphere, because you want to figure out the volume of the portion that's being removed. So it's the sphere that's going to determine your limits in z. And then the fact it's a cylinder, that's how you get your limits in r and theta, the other cylindrical coordinates. So here we have center sphere, radius of 1, so it's the hole you're cutting out, and being the radius of a sphere. So this distance, this is r equals 1, whereas here, coming out just this far, that's like r equals a half, and a different value of theta. So for any given r, in a situation like this, where this is again 3, this is r. And this is z.
Do you have a separate R?
What?
One was R equals 1, and another was R
Oh,
equals
yeah.
half.
Right, but so the thing is, really it's the same r, but this particular point has a different value of theta than this one. So for instance, depending on how we look at sphere, this could be theta equals 0, this could be theta equal pi. Yeah. So that's what you have to ask is which values of r are you covering? Which values of theta are you covering? Because you're moving a cylindrical hole. And then which values of z are you covering? Well, the sphere tells you that. So this is about spherical coordinates. So you have this portion of a ball of radius 2. So what are going to be the values of rho, theta, and phi that are going to be included in this portion of the sphere? So it's about understanding the ranges of spherical coordinates and what corresponds to what. And then the formulas for mass and center of mass. So you're given a function for the density. So we just concern ourselves with the first octant.
The lovely first octant. The only one defined explicitly, right?
Yeah, no one knows or cares what the other octants are. Okay, so if you see which values of r, theta, and phi, count for this, and then if you have any point that's within this, the density is the distance between the point x, y, z, and then the base, z equals 0. So that is your density function. So moments for the center of mass, you're going to have, for instance, mxy. That's going to be the triple integral over e of z, rho of x, y, z, your density function, dv. So then the z coordinate of your center of mass is going to be mxy over m. M is going to be the mass, where you're just going to integrate the density. So this distance, that's your rho of x, y, z.
So is that e like divided, like is the triple integral divided by e, or is that just kind of like just a notation?
Oh, yeah, so when we're doing like a double triple integral over some region, we just indicate what the region down below, like this. So it's kind of like a lower limit, if you will. So this is how you get the z coordinate of the center of mass, and then you do similar for the x and y coordinates.